In this video, we continue with Chapter 2, looking at problem solving and some skills that you'll need. First off, there are three things that you should know. First off, three laws that we discussed that led to the proposal for an atomic model: constant composition, multiple proportions, and conservation of matter. And then you should understand Dalton's atomic model and know the postulates contained therein. And then know the three key experiments that were critical in identifying atomic structure. That includes Thomson's cathode ray experiment, Millikan's oil drop experiment, and Rutherford's alpha particle scattering experiment. It's also worthwhile to know Thomson's rays of positive electricity and Aston's results. And for all these cases, you should understand the connection between either the laws or the experiments and the models that were derived from them. Now, we went over atomic symbols. Hopefully you're very comfortable with these. And so once we have a symbol, we can hopefully deduce some things about the atom. We'll choose a particular isotope in this case. That is the iron 56 isotope, and we'll look at the iron 3 cation. So how many protons, neutrons, and electrons are in one ion of iron 56 trication? And notice that the number comes before the sign, so it's 3 plus as opposed to plus 3. Pause and calculate that for yourself. Here we see the number of protons is 26. That's always the case for iron. Number of neutrons, therefore, has to be 30. It's 56 minus the 26 protons. So 56 is the mass number in this case. And then the number of electrons. Normally, iron would have 26 electrons. Number of protons equals number of neutrons, or number of protons equals number of electrons, excuse me. But in this case, we've got the trication, so we're missing 3 electrons. So we have 23 electrons. Next up, what ionic compounds form upon reaction of the following elements? These are ionic compounds that will be produced. We have a metal and a nonmetal. The key in solving this problem is knowing what are the normal charge states for the metals and the nonmetals in this example. Based on those charges, you'll know the smallest whole number ratios of atoms that need to be combined to form a neutral ionic compound. You don't need to balance the reaction. We're not going to balance them in this case. We'll deal with that in the next chapter. But in this case, we simply want to identify the chemical compound that is produced. So for example, with calcium, you're going to think, well, where's calcium on the periodic table? You pull your periodic table out, you see calcium is in group 2. You deduce that calcium normally has a +2 charge. Oxygen is in group 16, and so it's going to have a -2 charge. So one calcium and one oxygen, the charges would counterbalance one another. You're not going to write Ca2O2. You're going to write CaO. We want the smallest whole number ratios. Now, knowing that, go through and solve all 4 of these problems. Pause your video. Now note the equations are not balanced here. Calcium and oxygen form calcium oxide, CaO. Magnesium and fluorine form magnesium fluoride, MgF2. Magnesium has 2 plus charges, so I need 2 fluorines, each with -1 charge. Sodium and oxygen forms sodium oxide, Na2O. I need two sodiums to counterbalance the two negative charges on oxygen. And finally, lithium and chlorine form lithium chloride, LiCl, each with a +1 and a ± charge. These are more easily named because each of these metals in this example has only one available charge state. So we don't need to write, for example, magnesium 2 fluoride because magnesium always has just a +2 charge. So we will write magnesium fluoride as the correct IUPAC nomenclature. Moving on to binary ionic compounds. We looked at these thinking about the fact that in some cases, as we just saw in the last slide, we only have one charge state. And that would be the case for like calcium and bromine, forming calcium bromide. But then there are some cases where things have multiple charge states. For example, copper commonly has +1, +2. Lead is +2 and +4, like in your lead storage battery. So as we look at compounds, we need to identify where in the periodic table our elements are lying and if there's more than one charge state for that element. In this table, we have names and formulas for ionic compounds. You can complete this table as practice working on the rules that we've just gone over. Once you've completed the table, then you can restart the video and we can compare with the correct answers. Our first compound is Na2O. Na is the metal sodium. It is in group 1. It has only one available oxidation state, which is +1. Oxygen is a nonmetal, and in this case, for the ionic compound, we'll identify that as oxide, and of course that has a -2 charge, hence the Na sub 2 0 or Na sub 2O formula. So this name for this compound is sodium oxide. Next up, we have manganese 2 sulfide. Manganese is a transition metal. In this case, it has a +2 oxidation state. Manganese has many possible states. Sulfur is the component that gives us sulfide. Sulfur is a group 16 nonmetal. It has a -2 charge in binary ionic compounds. With manganese at +2 and sulfide at -2, we simply need one of each of these elements to have an electrically neutral system. Therefore, we have Mn(S) as our chemical formula. Our third compound is CaCl2. Calcium is a group 2 metal with only one available charge state, and that is +2. Chlorine is a halogen, group 17, with a -1 charge. Hence, we need two chlorines to counterbalance the calcium charge. In this case, there's no ambiguity in simply saying calcium chloride because calcium has only one possible charge state. Finally, we have potassium iodide. Potassium being a group 1 metal with only one charge state. We don't need to identify its oxidation state here. We call this potassium iodide, recognizing that potassium is +1. Iodine is in group 17. Hence, it has a -1 charge. For iodide, with a +1 and a -1 charge, we simply need one of each. Therefore, we have Ki for potassium iodide. Remembering the common polyatomic ions and their names and formulae, we want to have these very well recognized. I would suggest memorizing these, but committing to memory will not be essential in this class, as you'll be able to have access to this as part of the online exam. But it'll make it a lot easier if you do know them off the top of your head, and Knowing the charge states will make a lot of work throughout the semester a lot easier. And the same goes for the oxoanions. If we look in this upper table, some of the oxoanions are listed. But here, this is general, and you can imagine sticking in chlorine, bromine, iodine, sulfur, nitrogen, phosphorus, arsenic, selenium, so forth. We went over naming of acids and conceptual issues here. We have binary acids, which are HX. We have a hydrogen atom and another non-metal atom. Typically, these are covalent compounds, but when they dissolve in water, they turn into acids and they release protons. So, for example, hydrochloric acid, you can buy it as a gas, you can buy it in a gas tank, but as soon as it hits water, it turns into strong acid. And of course, if you breathe hydrochloric acid, you will experience this as soon as the hydrochloric acid hits your moist mucous membranes. Next up are oxoacids, and we've gone through the rules on these. We won't repeat those here. You can take a moment and look at them if you like, and we'll do some examples in a moment. Here's a table with some acids, a few oxoacids, and of binary acids. Complete the table with the correct name or formula, whatever is missing. So pause the video and see if you can figure out what you have here. Here are the correct answers. H2SO3. SO3 is sulfite. So ite becomes OUS acid. This is sulfurous acid. Next up, nitric acid. Nitric IC acid comes from the ATE ion. That's nitrate, so that has HNO3. NO3 is nitrate. We need one proton to go with that. Next up, H3PO4. PO4, 3- is phosphate. Therefore, the name is phosphoric acid. Those three are oxoacids. Next up, we have a binary acid, hydroiodic acid. That's simply HI. And finally, HF, which is hydrofluoric acid. Next up, we have binary covalent compounds. We know how to name these based on the prefixes as we discussed in our last video. So we'll have an example now after our prefixes. Remember these. Here are our example problems. Complete the name or the formula that's missing in the table. So pause your video, take your time, and complete the name or formula that is missing. N2O4. We need 2 nitrogens, so it's dinitrogen, and 4 oxygens, so it's tetraoxygen. Oxygen is the second element, so it's an oxide. Dinitrogen tetroxide. Next up, we have carbon disulfide, so we have a carbon and 2 sulfurs, CS2. Our third one, CO, is carbon monoxide. You might think monocarbon monoxide. But carbon monoxide is the name that you will see. Finally, hydrogen sulfide. To get the formula here, you need to recognize that sulfide is a 2- charge. Hydrogen has a +1 charge, therefore I need 2 hydrogens to make a neutral compound, H2S. Finally, there's the straight chain alkanes. We won't put any examples up. There's just a short table. But it's important to know those because that naming scheme is the scheme upon which all of your other naming will be based. So alkenes are built off of that, alkynes are built off of it, carboxylic acids, ethers, esters, and so forth. That completes the Chapter 2 videos. Next we move on to Chapter 3, where we take a closer look at quantitative aspects of chemistry.